Hi 8th grade Trailblazers, let's try this again. This is your one and only video for the week of September 21st. It's on math and metric system basics. This should be a review for you guys, but I expect you to know it, and we're going into chemistry, so I just spend a few minutes going through the video to make sure you're on the up and up with all this good stuff. Alright, so the metric system, you guys should know this based on a base unit of 10. You should know the base units, so meter, liter, gram. You should know that all you do to make up the specific measurement you want is to add a prefix to the base unit. For instance, you can do centi plus meter gives you centimeter, kilo plus liter gives you kiloliter, so on and so forth. So the three prefixes that we use mostly in science class are kilo, centi, and milli. However, I expect you to know all 6 of them. So there's different names: King, Henry's daughter, drink, chocolate, milk. There's all kinds of funny things to help you remember them. I can tell you right now, when I have to do conversions and I'm not using my Google conversion thing and I have to do it by hand, I still write this prefix bar at the top of my paper, so I make sure I'm not doing things wrong, and there's nothing wrong with that. I mean, actually, that's pretty smart to make sure that you're doing things the way that you should. All right, so let's talk about measuring length. So if I would measure length, I'm probably going to choose my meter as my base unit. So like the length of a tree branch is around 1.5 meters. The length of a room is generally around 5 meters. If I take a length of ball of twine, stretch out, it's around 25 meters. Those are things that we use meters for. But what if we needed to do something much bigger, like the distance from your house to school? Let's say you live approximately 10 miles from school. If I did that conversion from miles to meters, I would find that 10 miles is 16,093 meters. So if you say to your friend who's never been to your house, hey, come over, I'm having a sleepover, I only live 16,093 meters, and you're like, yeah, no, I'm not coming over to your house. It sounds crazy. Instead, what they do in other countries that use the metric system is they're just going to add a prefix onto that base unit so it's easier to manage. When you do that, 16,093 meters becomes 16.093 kilometers or 16.1 kilometers. Hey, I live about 16 kilometers away. That doesn't sound as bad as 16,093 meters. Yeah, nobody wants to come to your house when you live that far away. All right, the prefixes are based on the powers of 10. What does this mean? It means really silly in this country to not use the metric system. You guys went through all that horrific parts of like 3rd and 4th grade when they're like, how many things? Sally has 6 cups of milk, and Judy has this many, and how many gallons do they have if Ethel brings some more? I mean, like, it's just silly to have to convert from gallons to cups to it's just nonsense. So the metric system makes it easier. You're just, as you move up and down the scale or the ladder, it's either 10 times larger or 10 times smaller. So you can either do dimensional analysis, and I think you guys have done that in math, which sounds really hard, but you know it's really easy. So you can do dimensional analysis. That's one way to convert in the metric system. Or you can just divide and multiply by 10. Or you can just move decimals over. So whatever works for you. All of our brains work different. So me, I still just move the decimal over. All right, so we know that centimeters are 10 times larger than millimeters, so it takes more millimeters for the same length. And the thing that we're starting Wednesday, the metric spiles, the art activity, I'm making you work with millimeters or centimeters so that you guys become very accurate and precise, because you're not always accurate and precise, because you just want to be like, it's somewhere around 40, instead of telling me that it's 40.3 centimeters. You're going to be like, it's 40. It's not 40, it's 43. So we're going to work on getting that correct here. All right, so for each step to the right, you're multiplying by 10. So if I look down here and I start at decameters, and I just want to, how many meters is 5 decameters? I'm just going to move my decimal point to the right one. So 5 would become 50. Easy. So 5 decameters is 50 meters. In my example, I start at 1 liter. I want to go to deciliters and multiply by 10. So 1 times 10 is 10. Awesome. If I want to find out how many centiliters that is, 10 times 10 is 100. Super easy. I know you guys did this last year. So an easy way to move within the metric system is by moving the decimal point one place for each step desired. So if you're not really good at dimensional analysis, if you don't trust your Sorry, I didn't mean to pause you guys for a second. So this should be, so if you're not good at the math part of it, if you're not really good at the dividing or the multiplying, hopefully you're very good at just moving decimals, because that's all you have to do. So if we take that one we did, our previous example of your house being 16,093 meters away, all I did to get to 16.093 kilometers is move my decimal. So if I'm going from meters to kilometers, I'm moving first 1 over, so I move my decimal from this part outside the 3 in between the 9 and the 3, and then that's from meters to decameters. If I'm going from deca to hecto, I'm going to move it again 1 more, so that's going to give me 160.93 hectometers, and then if I just move it 1 more space, it becomes 16.93. Super easy. Alright, so if you move to the left in the diagram, you move the decimal to the left. If you move to the right in the diagram, you move the decimal to the right. Simple, simple, simple. Alright, so if you start from centimeters and convert to kilometers, if I have, again, I'm just counting how many spaces I'm moving. So I'm moving my decimal 1, 2, 3, 4, 5 spots. So that gives me 4 kilometers. So converting from meters to kilometers, again, if I'm moving to the left, I move my decimal to the left. I'm moving my decimal 1, 2, 3 hops, 4,000 meters becomes 4 kilometers. And if I go to the right, I just move my decimal to the right how many times I hop. So if I go from meters to centimeters, that's 1, 2 hops, 5 meters, 1, it becomes 500 centimeters. And I'm going to skip this because this should be just repetition to you guys. Pause it if you need to. Alright, so the summary for this is the base units in the metric system are meter, liter, gram, seconds, you know, all the basic units we use. It's based on the powers of 10, which means you either multiply, divide by 10. Easy. If you want to use the conversion method with this like ladder I just showed you, every step is 1 decimal place to the right or the left. So if you convert to the right, you move your decimal point to the right. If you move to the left, you move your decimal point to the left. Easy. Alright, so let's talk about some of the skills that I expect that you already know or that you should be using in here. The first one is estimation. So pretty easy. We're going to use estimation when we need to figure out how many things are in a group, and that group is just really too large for us to count. I'm not going to guess though. I'm going to section off my thing. I'm going to count. Maybe over here I count, 5 shapes. And then maybe I say, okay, there's a total of 6 boxes. 6 times 5 is 30. Maybe there's 30 shapes. Maybe, you are going to base it on reasonable assumptions. You're just not going to guess wildly. All right, accuracy and precision. This is super important that you guys understand the difference. I know you learned it last year, but I just want to go over it again. So when I talk about accuracy and precision, the first thing you have to understand is, especially chemistry, which we're getting into, is each element on the periodic table has its own physical properties, meaning it has its own fingerprints that are unique to that element or the molecule. So for instance, water is hydrogen and oxygen together. Every time they bond together, if I wanted to find the density of pure water, it's 1. It's an accepted value. They believe it in Bolivia. They believe it in, Iceland. The density of pure water is 1. If I ask you to find it in the lab and your measurements come out to 1.2 grams per milliliters, you might be like, there's something wrong with it. And there might be. The reason is the water that comes out of our faucet isn't pure. So that's probably accurate when you get 1.2. So maybe I ask you to find the density of water. I just want to make sure you guys get it. I ask you to find it 15 times and you have to do 15 trials. And you keep getting 1.2, 1.21, 1.19, 1.21, 1.20, and you get that over and over again. Well, you're not going to be very accurate. Your results aren't accurate because they're not very close to 1. 1.2 might sound close to 1, but it's really not in science. But you're going to be precise, meaning that all of your answers are really close to each other. So accuracy means how close we are to the accepted result. Precision means we could be totally not near the accepted result, except all of our answers are really close together. So what we would hope to find in our research and our investigations is that we're both accurate and precise. So what we would hope if we found the density of water, maybe I brought pure water in, is that our results were 1.0, 1.01, 0.99. That would be both accurate and precise. All right, significant figures. I'm not going to really, in years past I spent a lot of time on this, and it's super stressful for me because you guys, this isn't a standard, and your chemistry teachers can stress themselves out teaching it to you. But I do want to explain what significant figures are. So here's the deal. When I take a measurement with something, so say I take a measurement and I can go out to a really far unit. Like you guys do understand there's units much smaller than millimeter. There's nano, pico, there's tiny things. So that extends my decimal out to a lot of numbers. So if I have a very precise, high-powered tool that measures something that's 1.0004, that means that I've gone out all those digits. That's how precise that measurement is. Those are significant figures. So significant figures are used to communicate how precise our measurements are. So significant figures include all the digits that we use. So for instance, when I look at my rules for counting significant digits, here's the deal. All my non-zero digits, so non-zero is 1 through 9. And any zeros so all non-zero digits are always considered significant. So if I take a measurement and I have a 3, I have a 4, I have a 6, I have a 2, those are all considered significant. But if I have non-zeros between, if I have zeros between my non-zeros, they are also considered significant. So if I look at this number, 300042, because the 3, 4, and 2 are non-zero numbers, they're all significant. Also, because the zeros are between non-zeros, they're significant. So in this one, there are 6 significant digits. In this example, on the bottom, my leading zeros don't count. That means they're just there as placeholders. So that 0.0000, they're not considered significant because they're just there as placeholders. In this example, only 2 of the numbers are considered significant, and that's the 3 and the 4. Trailing zeros, however, do count if there's a decimal point. And the reason for it is that my measurement went out that far. That's how precise my instrument was, meaning that's significant. So while these zeros are just holding place, these are actually still measuring. So in this example, there's 4 significant digits. Don't worry about the last bullet because that's it just depends on who you ask. So when we add or subtract significant digits, the answer must have the same number of digits after the decimal as the measurement with the fewest number of digits after the decimal in the problem. So we'll do an example on the next slide. Multiplying and dividing is the same rule. So let's look at significant figures in addition and subtraction. So answer is always rounded to the same number of decimal places as a measurement with the least number of decimal places. So for example, 13.1. All of those digits are significant. There's 3 significant digits in that number, in that measurement. 4.25, 1, 2, 3. Again, there's 3. So our answer must be rounded to 3 significant digits. So if I do the math, oh, I'm sorry. Then I added another number, 63.408. 1, 2, 3, 4, 5 significant digits. So 3, 3, and 5. What's the least amount of significant digits? 3. My answer has to be rounded to 3 significant digits. So even though I get my answer in 5 significant digits, 80.758, they're not all significant. We have to round it to 3 digits. It would be 80.8. Multiplication and division is the same thing. So if I start with 4.3, both of those are considered significant. So there's 2 significant digits in that measurement, and it's multiplied by 2. There's only 1 significant digit in there. So my answer has to be in the least amount. So 1 is less than 2. So my answer has to be, even though I get 8.6, I just round it to 1. So it would round to 9. I would write that on my paper. On the division example, 18.75, all of those digits are considered significant, so 4. So 4 significant digits divided by 2 significant digits. 2 is less than 4, so I'm going to round my answer to 2. So 18.75 divided by 3.5 gives me 5.357, but that's 4 significant digits. That's too many. We have to round it to 2. So 5.357 becomes 5.4. Pretty easy. I'm going to give you a couple of these on an assignment just to practice, but we'll work on them together in class before you go home. All right, scientific notation. Hopefully you guys remember how to do this. Scientific notation, you have to keep your number. So what happens is this, I might get really big numbers or really tiny numbers, and I don't want to write them all down because it just becomes too many zeros, especially when like I'm studying cells or I'm studying atoms or I'm studying something really big like distances in space. So I would want to put it in scientific notation. So since you guys know it, I'm going to go really quick. You just know that it has to, when you make your number, it has to be between 1 and 9.99999. So it can't be less than 1 and it can't be greater than 9.99999. So in this first example, you guys just pause me for a second. Do this really quick. See if you guys get the right answers. If you do, awesome. If not, just know that we're moving the decimals to make the number between 1 and 9.999. So you're counting how many spaces you move the decimals. Awesome. All right, negative numbers are just the opposite as the positive scientific notation. You're just giving them negative exponents. So if you want to go ahead and pause it, try the 4 on the bottom, be my guest. Pause me now. I guess I took them out. All right, real quick. Mean, median, mode, and range. I expect you guys to know it, so I'm just going to spend a second going over it. I find that when I make assumptions, it just bites me where it hurts, and that's not fun. So the mean is just the average. You add all your numbers up, you divide it by your total number of numbers. The median number is the middle in an ordered set of data, so you got to go from least to greatest. If you have an odd number of numbers, it's the one smack dab in the middle. If you have an even number of numbers, you have to average those two in the middle together to get your median. Mode is the number that appears most often, so there may or may not be a mode, and the range is the difference between the greatest and least value in a set of data. All right, I think it's the last slide, and it has to do with reasonable and anomalous data. So reasonable data is data that we expect to find. Hopefully when we're doing our experiments, there is a reasonable amount of data. Oh yeah, that makes sense. That supports what we're learning in class. That's awesome. But once in a while we get one that you guys in math might call an outlier. It's called an anomaly. An anomaly is this piece of data that just doesn't fit anything else, and there's tons of reasons why we could have an anomaly. Maybe on that trial, we messed something up. Maybe we turn away for a second. Maybe we didn't do a step. But it happens. What you don't want to do, what a lot of people do is they just like erase it from their sheet and pretend it never happened. Don't do that. Report it, put it in your chart, graph it. But when you do your conclusions, okay, so I'm not quite sure where I left off. It's been a few minutes because I just started a new class. But so the whole point is a lot of times people want to like disregard the anomaly. They don't want to record it on their lab sheet or include it in their data charts or their graphs, but do it. Just put it there. And then you can do calculations like this where you use the anomalous value and you do it without. So include it, but when you do your conclusions, just know that probably something went wrong. And if you were precise and accurate with the rest of your measurements, you're probably right on target. Percent error is how do we know if we're precise or accurate. So this is a simple math calculation. In percent error before, I think your math teachers call it something else, but it's a really simple math calculation. It's just your theoretical value. What should you have had? Remember for water, we should have gotten 1. And then what we did get, maybe we got 1.2. So we would do 1 minus 1.2 over 1. That would give us a negative number. So do you see that it's in absolute values? So we would just change it to a positive. We would take that decimal, multiply it by 100, and that would give us our percent error. So if we have a low percent error, that's good. If it's like 5%, 6%, that's really good. That means we're pretty accurate. If our percent error is like 45, 60, that's not good. That means we were pretty inaccurate. So we want to try to aim for a low percent error. And that's all I got for you guys. Have a good week.